Can you hear me all right?
Yep. Yes.
Okay. All right, thanks. Well, let me share the screen. Okay.
Tom, we see your screen, but I don't hear you.
Hello, can you hear me now?
Yes.
Ah, sorry.
Yep.
Okay, I'll start from the beginning. Tonight I'm going to talk about the possibility of doing unguided imaging using astrophysics, sky modeling, and tracking correction capabilities. So this pertains primarily to astrophysics mounts. So if you have Celestron or Skywatcher mounts or other mounts, it really isn't all that relevant. Some of the mounts, like 10 micron, have their own similar systems, which are more integrated into the mount itself, as opposed to separate software packages. So this would pertain to mounts like the Mach 2, 1100 Go 2, and so forth. And the whole thing pertains both to creating and using pointing models to move your scope around this. Pardon me? Can I?
If you are not speaking, could you put your phone on your system on mute?
Okay. So this pertains both to pointing and tracking. So when you make a sky model, it can be used both for moving your scope around the sky to find objects and observe them, or to do imaging with tracking corrections. So you don't really have to use guide scopes and off-axis guiders and things like that. Let's see. So I'm trying to move the slide here. Let's see. Oh, there we go. Spacebar didn't work. First, I want to start off with a couple of definitions so things can be clarified a little bit. The whole topic is a little bit confusing when you first approach it, when you first get a mount and you start going through all the manuals and reading about usage of APCC Pro and these other utilities. Things can get a little hazy, so I'll just try to make some definitions. APCC Pro is astrophysics computer control. It's the user interface that controls basically all aspects of your mount operations. And it's the software that creates the actual sky models using points that are obtained or mapped by what's called APPM, or Astrophysics Point Mapper. That's a utility embedded within APCC Pro. And that is the utility where you measure where the scope is pointing in real life versus where it should be theoretically pointing if you had a perfect sky model. And then for imaging particularly, you have APCC tracking correction. That's an on-the-fly correction algorithm to send signals to the mount to keep everything centered up and have good tracking. But there's also a secondary tracking capability called declination arc tracking. That's a proprietary algorithm written by Gregg, which supposedly, and I believe does, improve tracking versus using a PCC tracking by itself. So the equipment and installation here, part one. This pertains again to all astrophysics mounts. It does not have to be an encoder equipped mount. It can be a non-encoder mount, a regular servo motor mount, such as an AP900. Some of the other manufacturers, I think, are like Mathis and Parallax. They use an AP control box of one sort or another. So some of those mounts are capable of utilizing this technology. But it does require astrophysics control boxes, either the go-to CP2 all the way up through the CP5. I know with the CP2, it does need some upgrades to the hardware, I think a different chip. So primarily most users are CP3 through CP5. And the CP5, I believe, is proprietary to the Mach 2. It comes automatically with every Mach 2. As far as software and drivers go, it's fairly straightforward. You first install your latest ASCOM platform off the ASCOM website. Then you need to install the latest version of the astrophysics firmware driver. I believe that's version 5.09, I believe, at this point. And then you install astrophysics computer control in that order, and then it'll all work nicely. You do need to have the APCC Pro version. They have a standard version. You can download that and check it out, but it does not include the ability to do unguided tracking. You also need to have your normal camera control software. I use the Astrophotography Tool, use Nina, other packages. And you also need a plate solver because you're going to be using plate solving to do the point mapping to create the sky models. I use ASTAP. It's an excellent package. It works very quickly and very versatile. And there are some others as well. A recommended accessory that astrophysics recommends, and I do as well, is a temperature and humidity sensor. These are little sensor boxes that you can pick up from, I think it's a company called Practical Solutions, for about $150. It provides your temperature data, both during the mapping process where you're creating your map for the sky model, as well as when you're using the map that you've created for active tracking. So on the fly, it's correcting for things like refraction as the temperature changes. Maybe it drops through the night while you're doing the imaging run, and it's feeding the temperature data into the model in real time to tweak and improve the correction factors. So for example, temperature on the right side there, as temperature changes for every 3 degrees centigrade, refraction changes 1%. So if you start off imaging at night and it's 20 degrees centigrade, say a fairly warm night, but through the course of the night, the temperature drops down to 5 degrees centigrade, that'll result in a 5% increase in refraction. And that could be fairly significant, and it's one of those inputs that's needed to obtain the best possible tracking model. As well, altitude makes a difference, air mass. I normally image down to about, 30 to 35 degrees, but even at 35 degrees altitude, you still get a couple of arc minutes of refraction occurring there. So as the mount moves toward the horizon, that refraction effect can start to significantly affect the quality of your sky model. So it is important to keep those environmental factors in mind. The other thing that affects the quality of your sky model is polar alignment. I use a right angle polar alignment scope from astrophysics. It's a very handy unit attached to the right side of the Mach 2. Comes on and off. It's a very quick and easy way to check polar alignment. I first did a drift alignment of the mount, and then I double checked it with the PoleMaster run, and they coincided very well. So then the objective was to tweak the position of the reticle in the ROPUS so it's in the proper position at the given time that you're checking it out. So the little graphic up on top left there is the astrophysics utility. You can get that on your phone and check it. It's a real-time utility that tells you where Polaris is located on the reticle, indicated by the yellow dot there. So you just make sure that that's in the proper position. And if it is, you're good to go. Center picture there is, that's the Mach 2 sitting on a Low-Samandi heavy-duty tripod, and I happen to have the RASA 8 scope sitting on it at the moment there. I use Telegizmos covers, incidentally. They're very handy. So once I get this mount aligned and operating well, it's pretty stable. There's no need to fiddle with it. So I just put a cover over it. Of course, I take the optics off, bring them in the house, but leave the mount out there. And from night to night to night, it retains polar alignment perfectly well. So you don't have to constantly tear apart everything and reassemble it each night. Now, this is a fairly important concept here, or understanding. A sky model accounts only for the reproducible or systematic factors in your payload. You got to remember that your payload, your scope, your mount, all the equipment, the cables, everything on a microscopic scale moves. It's fluid. There's gravity vectors that take place. As the scope moves around, those vectors change. And those things are all bending and twisting the payload, your camera, and so forth. And those factors have to be accounted for if you're going to create an accurate sky model. So things like polar misalignment, flexure, sagging, tilting of equipment, optics not being quite stable, refraction that we talked about, and things like dragging cables and so forth are all inputs to a model. Those result in flexure and movement of your equipment, which is then sensed by your optics, your camera. And that information is recorded in the mapping process, and it has to be accounted for. It has to be compensated for in your model to assure the highest degree of accuracy. But a model cannot account for what I call one-off issues, things that happen one time, bumps and wind blowing or some such thing happening where it's not a reproducible phenomenon. This is the graphical user interface of APCC. Laser pointer here. Right now I've got the yellow tab here is the pointing model tab. There's all these different tabs for different purposes. I won't get into those right now, but when you click on the pointing model tab, this upper half of the window becomes the information about pointing and tracking. So what you've got is up in the upper left here, you can enable the pointing correction. That's just for use for going one object to another. Enable your tracking correction. That's the inherent APCC tracking algorithm. Here you have your temperature input that's being actively monitored and changes via your THUM unit that you've got plugged in. The tracking correction status shows in real time what the changes are to the right ascension and declination axes, the corrections that the sky model has determined are being fed in, and you can actively monitor those changes. And they're updated every 1 second, so nearly real time. And then over here you've got the results of your point mapping that you did for the east and west horizons. These dots represent the map points that you collected, and it's calculated errors based on those positions, and those errors are input to the model and compensated for. Then another handy utility is the 3D view. Press the 3D view button here and you get this graphic, which shows the position of your scope in real time. So as you slew around or move around, you can keep an eye on the position of the scope and see if there's any possibility of ramming into the pier or some other problem happening. So it's a handy tool. Go back here. There's a button here, APPM. That's the Astrophysics Point Mapper. That's the button you click when you're ready to start your mapping process. When you click that, this menu will come up, Astrophysics Point Mapper. There's a number of tabs here. Well, these are just basically setup tabs for your camera and the plate solver. The most important one here at the moment is the measurement points. This is where you set up your map. It comes with 3 default maps that you can select, small, medium, and large. So small is 34 points, medium 101 points, large 256 points. So you can select any one of those that suits you. For most purposes, a small map will work just fine. I've found anyway for imaging. The more dense the map, of course, the longer it takes. So you have to balance time against accuracy. Once you have set up a map, you can then connect your scope, connect your camera, and you press start. And the software will now take control of your scope and sequentially move from one point to another in a logical fashion until it has acquired the data from each and every point. So in this case, there's 44 points that were mapped. And this process takes generally somewhere between 20 minutes up to maybe 50 minutes. Now, the result of the mapping process is what astrophysics calls their all-sky map. That's the entire sky. This graphic represents the sky. The horizon is the outermost circle. The innermost circle is a altitude or horizon limit that you've set yourself. I set it to be 25 degrees. And each of these points is the data point. Now in this particular case, this is a map that would take about, 428 minutes. That's, was that 7 hours, almost a full night to collect that map, covering both the east and west hemispheres. This type of map would be useful for a one-time operation. In other words, if you buy a scope, you have a concrete pier, permanent mount, observatory, etc. You might want to do a sky map like this one time, which has got plenty of data in it to do pointing and tracking under almost any circumstance. So it's something that you wouldn't want to do on a portable basis, but if you do have a permanent observatory, it's recommended that you might want to invest the time it takes to create a map like that. And once you've got it, it's stored. As long as you don't move your payload around, swap out payloads, bump things, take things apart, reassemble them, etc., the map then should be valid for quite some time. That you might want to check it in the future in case the ground shifts or some such thing, but generally it's almost a one and done operation.
What about seasons, Tom?
Pardon me?
What about seasonal changes? Do they make a recommendation that you do this once in summer and once in winter? I mean,
No, they don't make any specific recommendation like that. I think you have to probably just be cognizant of the environment in your particular observatory or location. Like, for example, in my location, the ground here is not entirely stable. It's it's somewhat fluid, and if that's really why I didn't sink a permanent pier, because I was afraid a pier might move around a little bit, and I'd be having more trouble with that than just using a good quality tripod. But there isn't any particular recommendation. I would say if you really get a freezing spell and then heat and freezing and heat, things like that, which can maybe shift and change positions and so forth of your equipment, even on a very small scale, then it might be a good idea to repeat that mapping process periodically. But that's a judgment call I think you'd have to make. As an option to an all-sky model, this is the more practical model for probably 90% of users. Partial all-sky model. This is where you map only a portion of the sky that contains the objects that you intend to image. Takes a whole lot less time. It's perfect for portable nightly setups. It's not useful for pointing because you're really only mapping a segment of the sky. So if you're going to try to point at objects away from that segment, your pointing accuracy will degrade versus an all-sky model. So this is really intended for imagers who are going after specific targets and specific locations. Now, they talk about the declination arcs. That might be a little confusing to begin with. What the heck is a declination arc? No. Well, it's not really that exotic of a concept. It's a series of map points along in east-west along the right ascension at a particular declination. So in this example, I've got 4 individual declination arcs. They're each spaced 3 degrees in declination. So each one is an arc. The collection of those arcs comprises the partial sky map. And the object that you intend to shoot, you would try to enclose or encompass with that segment of the sky represented by that grid of points. One thing to remember when you're using the partial all-sky map is to uncheck the enable pointing correction option in APCC, because you're not going to be getting good pointing accuracy if you only map a small portion of the sky. So you're better off just using your normal plate solver for pointing and keep that thing unchecked. Here's a little more detail of it. This is on the left here is the APPM menu for measurement points. And over here is the map. So in this case, the declination spacing has been set at 3 degrees. So we're going from 5 to 15 degrees in declination. The minimum or most southerly portion of the map that I want to create is at 5 degrees north over here. The maximum elevation or declination is 15 degrees. And then I've set a right ascension spacing here of 10 degrees. That's the spacing as we go from east to west. Once you set those parameters up, you can click show points, and it will produce this entire graphic here for you. Tell you how many points in total that you have, and also give you an estimated time it'll take to map all of those points and create for the input for the sky model. You also have to set some limits. So, for example, I mentioned before that the lowest I normally shoot in altitude is about 35 degrees. So here on the menu, I set up 35 degrees. That shows up as the white circle. And then you also have to set up a horizon limit. You might have trees, houses, things of that nature that block your horizon. So you can customize that horizon model, if you like, to account for those things. I happen to have a pretty good horizon all the way around, so I just set it at 25 degrees. And that's represented here by the circumference of the blue circle. So the area within, closed within the white circle here, is the sky that's available to me to use. And I happen to have a partial sky model set there. So here, for example, we take an object like NGC 7817. It has a declination of 20 degrees north. So in this case, I set a lower limit of 15 degrees in declination, an upper limit of 25 degrees, or a 10-degree span. And then in that span, I set the spacing to be 3 degrees and the RA spacing to be 8 degrees, creates 46 points, and that will take about 24, 25 minutes or so to create. So that object, NGC 7817, will be within this mapped area, and the sky model will generate the tracking corrections for this region and do quite a nice job in keeping it from having little egg-shaped stars. There's also a handy option you can do with a little planning, and I've done it several times. It's a custom map or a partial map for 2 objects in a given night. So let's say, for example, you've got an object at 3 degrees declination, represented here by the red star. And you got another object at 23 degrees declination. Well, it may turn out that, let's say, earlier in the evening, the first object at 3 degrees dec is pretty much overhead near the meridian, and it will be contained within my mapped region. And I can then track that from the meridian all the way down to my altitude limit of 35 degrees, probably about 3 to 3¼ hours or so. Well, by the time that object is in that position, object number 2 at 23 degrees declination will now have moved over to near the meridian, and I can simply slew from object number 1 right to that object number 2, and immediately begin imaging that with no fuss, with no setup of guide scopes or guiders or anything like that. Just instantly go to that object and begin an imaging run of that, which can then go for another 3 hours. And between the two, that's pretty much a whole evening. This is the result of that when you run APPM. Basically, what you're getting is a spreadsheet. In this particular case, I started collecting the map at 6:25 in the evening. It took about half an hour, ended at 6:58. And it's recording the right ascension and declination that the mount is actually pointing to. And then it's seeing what the error is, what the error is in both right ascension and declination. So, for example, the first line there, it's pointing at an RA of 23.764560 out to that many places. But when it does the plate solving, it comes up with with a slightly different number. So it calculates the error there and records that. It does that both for right ascension and declination. It also records the temperature at that point. And you'll notice that during that half hour that I collected the map, the temperature dropped from 11.4 to 9.8 degrees. So a temperature factor is included with each and every map point. So when you go back and use this map in the model, it is using this data, this temperature data, to correct, for example, the refraction. So it refines and accurizes the model to that extent. So it's quite sophisticated, actually.
So Tom, can we pause here for just one moment? Can you stay on that screen?
Yes.
On one back, yeah. So
This-
just a couple thoughts. The reason why I asked the question I did was because all those temperature points are mapped in there, and I would think that, seasonal adjustments are going to matter. But the more important thing that I see on here is that there's a shift between east facing and west facing. When the mount went west, all your RA errors went big. And I'm curious what you attribute that to. You see on the east side, you had less than an arc minute, more like
Mhm.
a half arc minute or less. And then when you got on the west side, pretty much everything was 3.5 to 4 arc minutes RA delta. Just
Yeah.
curious what you think about that. What does that mean to you?
Well, I haven't entirely figured that out yet. I've noticed that as well. It always seems to be low numbers in the east and higher numbers in the west. And generally, I'm collecting a lot more numbers in the west than I am in the east. That
Now, this
should
is with your Raza that you did this?
uh, no, actually, no. This was with probably a Ritchie Christian 8-inch.
Oh, okay. Because I
Okay.
mean, you can imagine flop, for instance, right?
Yeah.
Doing a meridian flip, but I don't know what else to attribute that to.
Yeah, I don't either, unless there's some systematic issue with the way the mount is positioned. I don't know. It doesn't
I mean,
seem
it's
to
well
matter.
behaved to the side, right?
Yeah,
So if
yeah,
you
yeah,
look at it, the delta on each side is not very much, but
yeah.
there's a big offset jump when you go from west to east or east to west.
Yeah, it's a big jump from looking at those numbers, but then again, you look at the absolute number. I mean, you're only looking at you know, a fraction of arc minutes here.
Yeah.
Error. I mean, the errors are quite small, and in other words, they are what they are for one reason or another, but they are being corrected for when
I'm,
the model is created and these errors are compensated for.
you look at that deck delta as an example, right? That's not flop dependent. And so, those are nice and small numbers no matter what side of the pier you're on. But at that east and west
Yeah.
RA delta is interesting. Okay, I'm sorry, I didn't mean
Yeah,
to.
it would be interesting to try, for someone else with the Mach 2 to see if they get this same effect. I don't know. It would be
Yeah.
uh,
Jeff could answer that question. He's ahead of me.
yeah, maybe so. Yeah, it might be scope dependent. I don't know. Most of the work I've done so far has been with the Ritchie Christian scopes.
Okay, thanks.
Yeah. So then let's see, go back here. Well, no, I went too far. So okay, once you finish the mapping process, you're done. It asks you if you want to use that data to create a model, a sky model. You answer yes, just a pop-up question that comes up. You answer yes, and then the model is created. So when you go to use the model, you can actually check it out and verify it. I've circled this area because these are the different factors that are being accounted for in the creation of the map or of the model per se. Index errors, non-perpendicularity of the OTA to the deck axis, for example, errors in the elevation and azimuth of your polar alignment, tube flexure, cantilever, and of course, refraction correction. So there's, I think, 9 factors there that it's accounting for when it calculates what the sky model is from that APPM data that you've collected.
Tom, have you ever checked any of those variables on and off to see what difference it makes?
Frankly, no. I've
Yeah,
had
I
this
haven't
mount,
either.
I had this mount since I think early November, and I haven't had all that much time to go thoroughly through this thing and experiment with lots of things. So I'm just kind of running with what it does and seeing what it does and trying to understand it a little bit.
But those properties there, they're all consistent with T-point for those who are familiar with T-point. And so some of those errors you wouldn't be able to turn off. So, or if they let you turn it off, you'd be in deep doo-doo, right? The index error as an example, or that probably shouldn't be turned off. And then I would think in general, you would want to keep almost all of them on. If you start reducing those properties, what you wind up with is a bigger error, right? It should be uniformly the case that if you start unclicking from the bottom towards the top, your pointing model error will get bigger and bigger.
Right.
Exactly the same as T-point.
Yeah. T-point. Yeah, and Gregg, like I'll get into this a little bit later, but he's put together this algorithm. I don't see any reason why you would want to start turning those off.
Right.
What the logic would be there. I mean,
Yeah, I was only puzzled by the fact that there are check boxes on the left.
I see.
It would just be locked on.
Yeah, it says model properties. You've got a model. I guess you could uncheck those and
Yeah, you got
degrade your model and
right.
experiment and find out what you could get rid of without starting to have bad tracking. But I would just assume leave them all on because they work, I mean, why go
Well, you
back?
need more points in general. If you think about T-point, if you don't have enough points, let's say you only wanted to start with 20 points, okay? 20 points is probably not enough to give you good error bars on those lower check marks. But if you're doing a 50-point model or a 100-point model, then of course you would want all of them checked. So I think the issue there is that the smaller the number of points you have, the fewer of those check boxes you're going to wind up being able to use without having a significant error in those terms. Does that make sense?
That makes sense.
It's classic T-point. I mean, this looks to me like T-point.
Yeah, there's no doubt similarities here, but I think for most of you, especially when you're doing portable, these partial sky models, portable setups, etc. I think you're going to want to have everything checked because you're probably not going to be, you're not going to be collecting lots of points like you would with a large all sky map that takes.
See, I can give you a good example real quick. Look at the tube flexure, right? If you were going to take a DEC model and you were going to stay high in the sky, then that tube flexure value isn't going to mean anything because you didn't take any values that were down low to the horizon, right? Does that make sense?
Yeah, that's probably true.
Yeah. And so again, all of these are sort of related. I think in some sense, you have to be a little bit careful about keeping all of those on when you're only doing a DEC Arc model. If you're doing a whole sky model, then all of them make sense for sure.
And I've seen nothing in the instructions on DEC Arc modeling that says turn any of these off. And I've never touched.
Well, I think if you turn them on and turn them off, I think you'd see the errors associated with those parameters rise and fall appropriately, depending upon where you took your slice in the sky.
Probably enough time in this rabbit hole.
Yeah.
Well, also notice, I mean, there's these models and the instructions emphasize that these models are really comprised of two models, the east model, the west model. That's why they show the two separately. And you've got them listed here, and you've got the associated errors listed in these columns. So if you uncheck one of these, I mean, I think it's going to eliminate both of them, right? So I would think if you are, for example, well, I think if you're just going to be imaging something in the Western Hemisphere, I'm not sure how relevant all the Eastern Hemisphere numbers are. Probably not. But then again, if you uncheck it, both the east and the west are going to be unchecked. I don't think you can selectively just uncheck, for example, the east errors and retain the west errors. So, but it's something to play with. I mean, I guess you could experiment and just see what happens. So this is like the APCC screen when you're actually in the process of tracking. So at this point, I've unchecked the enable pointing correction. I'm using a partial sky map. Enable tracking correction. The temperature is being actively monitored. I set it for every 30 seconds to refresh. And the active tracking corrections are being listed in these boxes for RA and DEC. They're listed in arc seconds per hour. And again, they are upgraded or updated every 1 second. And I normally have DEC Arc tracking checked as well. So with both of them checked, I'm not sure if one, I think DEC Arc tracking is is dominant. I talked to Ray Graylack about that, and I'll get into that in just a very short time. But apparently, when you have enabled DEC Arc tracking checked, it is operating. You can uncheck it, and then the native tracking correction algorithm for APCC is operative. But the DEC Arc tracking is an improved algorithm. And so I think under normal circumstances, you'd want to have that checked. Then, of course, you have the correct for refraction box checked too. So you can sit here and watch the numbers change as the scope moves along. So declination arc tracking. Now, this is what the manual says. Excuse the wordy slide, but I think it's important. The DEC Arc tracking provides an alternative and usually more accurate way to calculate tracking rates from the data points in your data. Works by doing a best fit calculation of pointing errors at each declination accumulated in APPM. The rates are interpolated from each declination arc, providing an improved all-sky tracking rate correction compared to using the all-sky model. And the DEC Arc model accounts for all pointing errors, even those not represented in APC's all-sky pointing model, which may not be able to as accurately calculate tracking. So the DEC Arc modeling apparently accounts for some other factors beyond those accounted for by APCC tracking correction alone. So to get to the bottom of this, I contacted Ray Graylack, who's the programmer for all this stuff, and asked him some questions about this. So here they are. I said, once the DEC Arc tracking checkbox is activated, what's the process that adjusts the mount? His answer, well, with the DEC Arc tracking enabled, APCC continuously adjusts the mount's RA and DEC tracking rates instead of making tiny, discrete moves. And I took that to mean tiny, discrete moves would be things that, for example, a guide scope would do. You know, collect the image of a guide star, measure its position, issue a signal to correct the mount, one after another. So those would be tiny, discrete moves. Whereas APCC and DEC Arc tracking are constantly adjusting the motor speeds and position of the mount on a fluid, continuous basis, almost like adaptive optics, you know, would correct star position, mount position at a very high rate of speed. Also, what's the difference in the process between just running with the enabled tracking correction box checked, which is that native APCC tracking correction, versus also checking the enabled DEC Arc tracking box? Well, with just enabled tracking correction, it'll use the all-sky pointing model and calculate the rates. When DEC Arc tracking is enabled and the mount's pointing inside the region that you've mapped, like that partial map, a completely different algorithm is used to calculate the RA and DEC tracking rates. So it's a completely different algorithm. Well, I asked him what that was, and he can't tell me. It's totally proprietary. Astrophysics will not divulge information, and Ray Gralak will not give you any details about the mathematics behind the algorithm. So I thought, well, does the DEC Arc tracking include more corrections, more factors, cantilever, whatever, than the tracking correction alone does, and therefore is somehow more accurate or more complete? And his answer is, well, the all-sky model uses many standard pointing terms, and I think those are the list of 9 things that we saw there on the earlier slide to model the physics of the telescope, the vectors. But some telescopes can have behavior not covered by those terms. I'm not quite sure what that is all about. But anyway, whatever unique or strange things happen with some individual telescope might not be covered by those standard terms. So if that happens, pointing and correction rate may not be as good as they could be. So the DEC Arc tracking algorithm, proprietary, but I can say that it models points independently of the all-sky pointing terms to produce a better result. And it outperforms the standard tracking algorithm, except when the number of localized points is much smaller than the total number of points in an all-sky model. So if you've got very few points, or relatively few points in your partial sky model versus, say, the total number of points in the large all-sky model, then the DEC Arc tracking would not offer any advantage. But assuming that your partial map contains a higher density of map points than your all-sky model, or larger scale model, then the DEC Arc tracking will outperform it. And then the specific numbers depend on the characteristics of the setup, et cetera. Needs to be empirically determined through experimentation. So in other words, you have to fiddle with it a little bit to find out what pertains to your particular setup. So I had hoped that I could get a very clear explanation of exactly what the DEC Arc tracking algorithm is and exactly what advantages it offers mathematically over the standard tracking correction algorithm. But unfortunately, that information is not to be divulged by AP or by Ray.
Tom, have you seen a difference in your own experiments using all-sky versus DEC Arc on your system?
Well, to date, I have let's put it this way. During an imaging run, sometimes I will uncheck DEC Arc tracking and monitor what's going on. And I see very little change, no different. The stars are still perfectly fine. So I can click it on and off and not really see anything changing. They both seem to be pretty darn good. Now, maybe DEC Arc tracking is, in fact, mathematically better somehow, or maybe my particular system is so well behaved that it doesn't matter much whether I use DEC Arc tracking or not, but I can't really answer that.
I've got a shorter focal length than you do. At 660, but I same thing with me. I've done both. I get terrific results with both, but one is not obviously better than the other.
Right. Yeah. I think it's very system dependent, very individual system dependent, and you have to work with it a little bit. And you may find the DEC Arc tracking indeed gives you some advantage. But to make a general statement about it, I don't think is valid.
I mean, I smell a little bit of marketing there in that last slide. Not from you, Tom, but from AP. There are people who have spent their entire careers working on pointing models for professional telescopes, and I can see that not all the pointing terms are in the model that they give you there for the standard model, but there aren't that many more that are missing. So I suspect that he might have a few other pointing model terms, but yeah, I'd be very surprised if it's dramatically different. Yeah.
Yeah, and
I think part of the advantage of DEC Arc is that it's a much denser model for the region of sky you're working in.
Yeah, no
A higher
question.
resolution model than an all sky model.
But
well,
the qualitative note that Tom made about, well, my stars look kind of round in both cases. Really what you'd like to see is you'd like to kind of monitor the actual quantitative deltas and see what they look like. And I suspect that it might not matter, right? Of course, by you guys are looking at the star shapes and saying, hey, it doesn't matter. So
well, that's
I
the
think
bottom line,
there's
right?
marketing there. Yeah.
Yeah, I mean, if the stars come out nice and round and long focal lengths, I'm happy. Um, yeah, okay. Well, yeah, there is some marketing and stuff going on there, but I don't think it's just that. Again, the DEC Arc tracking uses more uh, factors. It might, but I don't think that's just the difference. It's a completely different calculation according to Ray. It's a different algorithm. It uses all of the terms differently than the standard tracking correction. So what exactly is that in terms of mathematical definition? I don't know. But I did run this little graphic by Ray, and he said, "Yeah, that's exactly how it works, and at least the first order." So if here you have like a DEC arc shown in red. This is one of your declination arcs, and these blue dots represent the data points from your APPM mapping run. And say they're separated by 5 degrees in right ascension. So normally sidereal speed is 15.04 arc seconds per second. So 5 degrees, well, it would take 1197 seconds to go from point A to point B, the two green dots there. So if your plate solving shows that the error, the delta in RA is say 60 arc seconds, so in other words, the yellow dot represents what you actually get when you did your plate solving versus where it should be, represented by this right-hand green dot. Then the tracking error is 60 arc seconds divided by the 1197 seconds, or 0.05 arc seconds per second. So that's the correction factor. So your corrected right ascension speed then would be sidereal rate plus the 0.05 arc seconds per second correction factor for a total of 15.09 arc seconds per second. So that would be the tracking rate calculated between point A and point B to assure that your stars are tracked properly and come out nice and round. So that's just sort of a basic illustration of the correction that's being made in right ascension based on the delta in RA that was found by your mapping process. And then it's doing that from point to point to point to point all the way along the DEC arcs, and it's also doing it in declination at the same time. So it's fairly interesting process. So then the bottom line is, well, does all this stuff work? Well, what's the whole point of it? So I've got a few examples here I'll show, and I'm going to show the typical sub, that I take, and as well as the final result. So this is NGC 266. This is with the RC8, which you cushion 8-inch, 1612 millimeters. It's with the ASI 2600 pro color camera. So the resolution, this is at f8, and the resolution then is sub 0.5 arc seconds per pixel, so pretty good. This is the result of using a 34-point partial sky model, 18 to 40 degrees north. I had DEC Arc tracking checked. It's totally unguided. This is a typical 3-minute sub. I collected 90 of them. Every single sub looks exactly like this. Every star is perfectly round. Never had an out or round problem or any issue whatsoever. Stack them all together, you get a pretty decent image. Here's NGC 23, same setup, same focal length, same sky coverage. Again, unguided. This is a 44-point model. Again, DEC Arc tracking is checked. An individual 3-minute sub here shows that there's a little double star. The separation between the centroids on it, that little pair, is about 9.8 arc seconds. Nice clean separation. So there's no problem. I mean, it is perfectly round. So if there was any issue at all, you'd see a little egg shape or these things starting to merge together or some such thing. Here's another one, Heinz Variable Nebula, same scope, same setup. Another typical 3-minute sub, and then a portion of the final image, 210 minutes total. And I can unequivocally state right now that every single sub I've ever taken since using this tracking correction algorithm has been perfect. I don't have any issues whatsoever with any out of round stars or egg shapes or any other anomalies occurring. This is with the RASA 8. It's a lot shorter focal length, 400 millimeters. And when you drizzle process it, it comes out to sub 1 arc minute in resolution, 0.97 arc seconds per pixel. This is with a 38-point model that took about 20 to 25 minutes to make. And again, if you can do it at 1600 millimeters, you can certainly do it at 400 with no problem. M1 Crab Nebula. Here's again 3-minute subs taken with the RC8 at f8. I'm only using a field flattener with that scope, no reducer. And again, every sub comes out perfect. So it's very nice. You don't have to set up a PhD2. You don't have to fool with guide scopes. Figure out problems with guiding, flexure, all those kinds of things. Don't have to fiddle with an off-axis guider. Makes life very easy and much more enjoyable to do imaging.
Okay, Tom, I have a question.
Yes.
How do you dither?
Good question. In the astrophotography tool, under the guiding tab, they have an option called astrophotography tool dithering. And that's for when you don't have a guide scope. You have an active connection to your mount, and that's through APTT. So APT. So when you go to dither, you set it up just like you would PhD2, only the APT dithering takes over and will move your mount the desired number of pixels and set the delay that you like to have, say 5 or 6 seconds for settling, all the other parameters, and it will automatically dither the mount as you set it up. So you can dither every 1 or 2 or 3 or 5, whatever images, and go from there. So it's very nice. You don't have to use a guide scope. So this is the last slide here. The question I have now is, well, what about longer focal length optics? Well, I gotta have an RC10 here that I'm going to be using shortly. I've used it before on my 900 mount with guide scope. It's kind of a big guide scope. I got weight there and cantilever and balance and everything else that happens because of that. So if I can discard that, put the RC10 on the Mach 2 and do this tracking. Hopefully, you will get the same result. I don't see any reason why it shouldn't. If it works at 1600, should work at 2000. And then the other experiment I want to do later is to put up my 900 mount again, which is kind of in storage right now, and use APCC in modeling to set up sky models with that and see if I can improve the tracking. It's excellent now, very, very good, but it has a little bit of issue now and then that ruins a sub. So I normally do separate guide scope tracking with it. So I want to hopefully discard that, and maybe I can get the sky model and the DEC Arc tracking to work well enough that all or most of my subs will come out fine without the need for a separate guide scope. So those are things to be determined shortly. And let's see. Well, the other thing too is just for me, just in a sort of a practical thing, guiding is not a real big issue these days. It's not difficult. PhD2 is great, but you do have, the mechanical possibilities of flexure and other things happening. And you do have that system to work with and deal with and monitor and so forth. It's very nice to have absolutely no guide scope or guiding algorithms and guiding software to fool with. Just point and shoot, point and shoot, point and shoot, go from one object to another. Just set up your plan for your night with your tracking model and your mapping, and go from there. And it's quite enjoyable, actually. It's very nice. So I'd encourage anybody. And by the way, as again, you don't need an encoder mount. I just want to emphasize that. So if you have an astrophysics mount that's non-encoder, you certainly should, I think, give it a whirl. Try APCC and try the DEC Arc tracking and see what you get. So that's it. With any questions?
Hey, thank you.
Yep.
Tom, how long are these models good for if they're on a pier?
Okay, no, that's a good question. See, I talked to astrophysics about that. I said, if you create a good model that works, working very nice. I said, what happens if I take the scope off the mount, bring it in the house, and put the scope back on the next night? Is that model still valid? Well, they said probably not, but we don't know for sure. You'll have to try it. Well, I did try it, and I found it doesn't make any difference at all. The model works perfectly night to night to night. The only time that you'll have a problem is if you bump something, or if somehow your mount settles. One time I had one of the tripod legs dip a little bit, and I had to correct that. So the polar alignment was off, and so I had to create a new model. But unless something like that happens, if you've got a pretty stable setup, once you create a good model, you should be good to go.
Thank you.
Okay, Tom, if you could stop sharing your screen.
Let's see here. Stop share.
All right. Any other questions for Tom? Okay, I'm going to share my screen. And hopefully you can all see that. I want to spend just a couple minutes talking about the Astronomical League's Foundation of Imaging observing program. If you've done any Astronomical League programs in the past, you're probably familiar with the fact that these are typically kind of a challenge where they challenge you to really go outside of the normal things that you might be doing and do things a little bit bigger and better. And of course, the Foundation of Imaging program is kind of directed towards imaging. And you probably also realize that over the last few years, the Astronomical League has gone from a strict observing type of organization to one that allows imaging. So they have an imaging Messier program, Comet imaging program, and the Foundation of Imaging Observing program is kind of a program to challenge you to do all different aspects of imaging. And everything I'm going to show you here is directly from their website, which you see at the bottom here, for the Foundations of Imaging Observing program. So they tell us that basically there are three main reasons why people do these images. One is to create artistic images. The second is to aid in observing things that you can't really see very well with your eye, and that's why a lot of us got into imaging in the first place. And finally, some of us want to collect scientific data to extend the bounds of astronomical knowledge using purely linear data. And this program kind of addresses all of those aspects. So like most of the other Astronomical League programs, the Foundation of Imaging have these quick view requirements, and you can see here that basically this is a telescope and imaging type of program, and they do allow you to use images from a remote telescope. The total number of images that you would collect is around 53, not exactly, because I've noticed there's a few discrepancies, and there's just one level. Now, some of their observing programs have multiple levels, like the Comet imaging program. You can do the silver level or the gold level by doing more comets. But this program simply has one level. You have to be an AL member, and the only special equipment that's really required is a solar filter, because part of the imaging program requires that you do some solar imaging. So on the left here, you see what the general categories of imaging targets are in the program. And it can everything from constellations, nightscape, meteors, lunar, solar, stars, planets, of course, deep space objects, comets, asteroids, and eclipses and occultations. And for each of these types of objects, there are certain requirements. And the requirements look to be pretty stringent, but I can tell you that for a lot of these, by how you submit your data, the coordinators are pretty easy to get along with in terms of what you have to submit. For example, the time of observation, since imaging may last over several nights or even months, that really doesn't make a lot of sense. And so if you tell them that I took this image over, a period of days, they don't really pay too much attention to the fact that you don't have a time of when you started the observation. You do have to have most of the other details there, including if you're using images from a remote telescope, the details of how that remote scope actually operates. So there's a couple general groupings. Solar system images makes up about half of what you required. And so there are various different images of the sun, the moon, the planets, Jupiter and Saturn, dwarf planets, at least one comet and one asteroid. The great thing about the program is that they've got these options. So if you've never imaged an asteroid, you can substitute a lunar eclipse image that you may have made, or a wide field image of the Milky Way. And so while they have some reasonably stringent guidelines for the types of images that they want to see, they have a lot of options. And so you have a lot of flexibility in terms of things that you may have imaged or haven't imaged but want to try to image, but you might not ever want to go out and try to image a dwarf planet-like Ceres. The deep sky part, it consists of about 25 images. So if you add up 25 and 27, you get 52. And again, this is the typical stuff that you might expect: open clusters, globulars, dark nebulas, galaxies, of course. And when they talk about galaxies, they throw in things like you have to have at least one image of M31. For bright nebula, they have a bunch of different region types that you have to have. But of course, you have to have at least one image of M41, M42. And then again, just like with the solar system objects, there's a various different optional things that you can image or may have imaged in the past that you can submit in lieu of some of the requirements. So that makes the entire program very flexible and allows you to meet the requirements for the 50+ images pretty easily. So what you have to report for each of these images in some fashion are the things that you see listed here. And all of those things are required, but as I mentioned previously, the program coordinators are pretty easy to get along with in terms of if you have the same exact field of view in every one of your images, you can just say the field of view for my images is this. And for the various different types of images, you may have to list those. What I did on mine was put them all in a spreadsheet and have different comments for different images so that the person who's evaluating your submission can see very easily that you've met all of these requirements for each of the images, even though the types of images may vary slightly from each to the other. So the way I do this, I put my images on a web page that I've had for the last 25 years or so. And again, I have a table below each image, and most of the information that's required for the Astronomical League program can be copied right off of the table that I have with each of my images. And of course, I can submit, that this image was taken at a particular location to meet that requirement. So that makes it fairly easy to submit your images in order to get the certification that you've met the requirements of the program. If you do all that, you get a handsome certificate suitable for framing, and you get the little lapel pin, which you can wear to impress your friends. So I encourage you to think about possibly looking at the Foundations of Imaging program if you want to widen your horizons in terms of the types of images that you're interested in taking. And probably you may have been taking images for a long time, like many of you have, and you maybe have a lot of these 50+ images already in your collection. It would make it very easy for you to go ahead and get the certificate. So I'll stop at that point, and if you have any questions about the Foundations of Imaging, I'll answer them. No questions?
Well, Greg, are they using these images for anything? Some purpose?
Well, yeah, you can submit these to the Reflector, which is the official publication of the Astronomical League. And so if you submit your images, you may find that your images get published, even on the cover of the Reflector, which comes out quarterly. I've had a couple of images published in that magazine.
Thank you.
Basically, it's for your own edification and enjoyment to get that certificate that you've collected a wide range of different types of images.
And what I understand that you can use images that you've already taken.
Yeah. Yeah.
For all this.
Yeah, you don't have to do it proactively. You can, in fact, most of the images that I submitted were images that I've taken over the last 20 years. All right, we're going to now switch over to something that we're going to try that was suggested in some of our previous meetings, and that is to have a kind of beginner's corner. And helping me with this has been Jeff Rothstein. He has gathered a few beginner's questions. So Jeff, if you'd like to take over for a minute and start us off with one or two of those beginner's questions, and we can open the floor and see what kind of answers we come up with.
Thanks a lot, Greg. And hello, everyone. Tom, nice job on the presentation. We solicited and received more questions than we're going to be able to get through this evening. If we don't get to your question, I invite you to post it to the chat and we can continue the discussion in the chat room. But the first one came from Sam Miller, who is starting to think about transitioning from MaxMDL to PixInsight. And he asks, has anyone ever developed a cheat sheet on processing workflow for beginners? The simple answer to that question, yes, Randy Smith. And I think Randy has already reached out to Sam directly to talk about that. But I wanted to, and Randy, I'd invite you to, maybe before I say anything more, to say a word or two about a standard, simple PixInsight workflow.
I guess what I've done for a few people now and then is just get the most simple basic tools that's available and just set them up and then email them the icons that they can import, they can open in PixInsight. But without going through them, usually what I've done is just on a one-to-one Zoom call, go through them, and maybe I may take an image and just let them watch, and then we can go through it again and let the other person drive, and I can watch and critique. Just a simple set without some hands-on instruction. I'm not sure how useful that's going to be, but that's what I've done a few times, and then otherwise it seems overwhelming. There's so much and so many ways to do things. So,
well, and Randy was kind enough to do exactly that for me a couple of years ago as I was starting to work with PixInsight, and the process has gotten simpler in the last couple of years as some of the new processing tools like the Russell Croman Blur Exterminator, Star Exterminator, Noise Exterminator have come along. They've replaced more complicated alternatives. The point that I'd like to add to what Randy said, when you open PixInsight and you look at all the processes and all the scripts, there's like 250 of them. It is absolutely overwhelming, but you can create really nice images with about 7 to 10 steps. And we are coming out of that supplemental meeting that we had a couple of weeks ago. We are putting together some beginner resources. And these are going to be links to YouTube or websites or other things that we all found useful when we were beginners. And we hope that you will find resources there to help get started in PixInsight as well. So very quickly, I thought I would just show you. Oops, not that one. No, I'm not finding it, so I'm not going to do it. But we are working on a couple of things that will help beginners in PixInsight. One is a mentoring program, and we'll have details on that. It'll be very informal. We'll provide lists of people and what kind of equipment, software they use, and these are people who are willing to answer questions or spend some time with you. And if you're interested in being a mentor, reach out to Gregg or me, and we'll get you added to the spreadsheet. And then also these beginner resources, which we will make available in the weeks ahead, we think will also help get you started. The second question, and thanks for that question, Sam. The second question we wanted to tackle tonight came from Steve Irwin, who is an experienced visual astronomer, starting to think about switching to imaging. And he's curious to know about imaging equipment, cameras and nomenclature, what camera goes with what scope, monochrome versus one-shot color. This is a topic that is at least as broad as the one Tom just walked us through this evening, and probably broader. I think we can get a couple of perspectives here. I'll lead it off by saying, I think the first question, if you're going to become an imager, that you got to decide is one-shot color or monochrome. One-shot color is fewer steps because you take one image and you get a color picture. Monochrome, you've got to build either red, green, blue, or hydrogen, oxygen, sulfur, or whatever other specialized filters you're using. It takes more time. The advantage of monochrome is 100% of the pixels are collecting the color that you are choosing to collect. Remember, in a one-shot color camera, whether it's a Nikon or a Sony or an iPhone or any of our Astro cameras, there is an array, a grid with tiny filters over the pixels. So 50% of your pixels are collecting only green, 25 red, 25 blue. And so if you're looking for a red and blue target, you got to shoot a lot more time than you would with a monochrome camera. There's more expense with monochrome because you're going to have to buy those filters right up front. But that's that again, with that topic in mind, I hope it'll help you go off and do some research on what might work for you. Others, please join in. What kind of hardware related issues, field flatteners or cameras or the like, does an experienced visual astronomer need to think about to start imaging?
Budget.
Lad, if you're speaking, you're on mute.
So a couple thoughts. I'll step in for a moment. I think just like with visual, an important thing for people who want to switch from visual to imaging is the age-old question that the visual people went through, which is, what do you want? What are you thinking you want to look at? What is it that you think you want to image? And based, that answer will drive you in a direction that will help you sort of pick the gear you're interested in. I will come back maybe to one thing you said, Jeff, and respectfully disagree with you a little bit about the Bayer matrix, basically, that you were talking about, this color filters that are sitting in front of those pixels on the camera. Green pixels, if you look at a camera, when you look at the technical specifications for all of those one-shot color cameras, they are all sensitive in all of the bands. They're not as sensitive. So for instance, those green pixels are not just picking up green, they're also picking up blue data and they're picking up red data. Now they're funneling it into the green pixels, but likewise, your red pixels are picking up some green data and some blue data. And so it's not quite the case that you have to image 4 times longer to get the same amount of data. You're getting some what I call color confusion, but it's not really noticeable if you don't know what you're looking at. And nowadays, people are mapping every possible color into whatever colors they want. So you are still getting the same amount of data. It's just that the color mapping may not be exactly as pure as it would be if you were taking data with filters. So I'll leave it there.
Thanks a lot, Doug.
Okay, I'll jump in and give you my take on starting off, and I think you touched on this real briefly, Jeff, is that the thing that many beginning imagers have a problem with is they've got a telescope, they want to hook a camera to it, and they quickly discover that the mount that came with their telescope doesn't allow them to do long exposure images. That's both a good thing and a bad thing. It's a bad thing if you want to take pictures of something that's very dim where you do need to take a long exposure, but it's a good thing if you decide, well, I can't really take 5-minute or 3-minute images because I don't have a good tracking mount like the ones that Tom was describing earlier. But it does mean that you can use a less than perfect mount to do planetary or lunar or solar imaging. So again, like Doug kind of alluded to there, if you think about what it is you want to image and think about what equipment you have at hand, many times that can get you started, even though that may not be your ultimate goal. Your ultimate goal may be to do images of galaxies, but if your mount will only let you take pictures of the moon, well, maybe you should start off taking pictures of the moon and develop your skills in processing as you go along. So,
I mean, to build on what you just said, Greg, I think taking pictures of the moon is a fantastic place to start. You can stick a DSLR on the back of your just about any telescope and get some decent pictures right away, and that lights the fire. When you start getting good pictures and something beyond what you can see with your eye, that's how I caught this bug, this incurable disease that we all have. But the other thing to bear in mind about equipment is if you read the Cloudy Nights and other chat boards, if you have a C14 and you've never used it for imaging, don't try. Get yourself a nice 80 millimeter refractor and learn how to do your imaging with something wider field than the kind of telescope that Gregg has set up in his backyard. So that's those are a few responses. Again, these are wonderful questions that we could spend an entire evening on. And I know we're coming to the bottom of the hour, and I think we wanted to wind up. I do have one more question that perhaps we can slip into this 4 minutes.
We have time.
We do. Okay. So the question is, and this one came from Kevin Shea. How do you handle light clouds at night? How do you tell you're encountering clouds other than lost star errors that you might be getting through your software? Gregg, you've been doing this for a long time. What do you do about clouds?
Well, I actually think that that's a positive way of looking at it. I use a guide scope, and when the clouds roll in, my guide scope declares an error and sends me a text message saying, the guide star has been lost. That's pretty generally either something goofy happened with the telescope, or most of the time it's clouds rolled in. And so you can have a camera pointed at the sky next to your scope, but if you're using a guide scope, or even if you're just using a regular camera with an unguided, if your software will alert you that something's gone wrong, you can stop the imaging until the clouds roll through, or you can stop imaging altogether if it looks like it's going to start to rain or snow. So I don't really see that as a terrible disadvantage, and I always describe my guide scope as my my cloud detector.
Yeah, also, if you are taking images and high thin clouds come in, which can be very detrimental to imaging faint nebula, dark nebula, very faint things, then generally you'll start seeing like a glow or a halo around the stars. And once that happens, you may as well wrap it up until that goes away.
I saw a picture. I don't know if it was someone in this group or elsewhere online. Someone had taken one of those little kind of R2D2 WISE cameras and stuck it where their guide scope otherwise would have been, and pointed it at the sky, and they could look at the sky. I don't know how good that is for seeing clouds, but you could try.
Mm-hmm.
I'd like to politely disagree with Jeff on one thing you mentioned a while ago. If somebody has a C11, first thing you would tell them is not to do imaging with it. Go get yourself a small refractor. First thing I would tell them is get yourself a hyperstar, because the easiest way.
But that's getting the same.
Yeah,
that's solving the problem another way. You're not using a 2600 millimeter scope.
Because the things that I try to get across to people who are looking to get a start, if they're coming from visual astronomy, they have no appreciation for speed in a camera. So I talk to them about the need for speed and the need for a wide field of view. A wide field of view and a fast camera is a very forgiving combination. And if you have a halfway decent mount at all, and as we all know, the most important piece of gear is the mount. The second most important is the dump, and so on. But if you've got a wide field of view and a fast camera to a telescope combination, that's a great way to start. It doesn't matter whether you're doing
Yes,
color, one-shot color, mono.
a good refinement. Thanks, Alan. All right, other thoughts on these questions for this evening? And we'd love to get feedback on whether this is helpful to those who have a little less experience. How can we make this better? This plus the other things that I mentioned that we'll have coming along are all going to be aimed really at making it easier for beginners to join us and work and create images like the one behind Alan.
All right. Well, thank you, everybody, for participating. And again, as Jeff said, if you have beginners' questions, be sure to submit those to him or I, and we'll do this again next month.
Yeah, next month.
All right. Thank you.
Thanks, everybody.